This is the intro video for Lab 5 of the Apsc 1299 labs, and this week we're studying oscillator speed and PWM, where PWM stands for pulse width modulation. Now I'll warn you that this is a bit of a long experiment, so don't leave it to the last minute. It's actually quite difficult to get this one done in 1 week. There is a pre-lab for this experiment. You should read the appendix in your lab manual about the oscilloscope. There is also a video on how to use the oscilloscope that you should watch. There's also 3 sections of the PIC 18F 4525 datasheet that you should read before starting the experiment. Where do you find the datasheet? Well, if you go to the course website, there's a link that says datasheets. So download what you need from there and then read the 3 sections that are specified here. Now the reason why this experiment takes a bit longer is because you have to use the oscilloscopes, and the lab room oscilloscopes cannot be taken out of the room. They must stay in the lab rooms, so you're constrained to working at school a bit more than usual. However, we do have 2 oscilloscopes that we put into the libraries, both at Surrey and at Richmond campuses, and you can sign those out in 2-hour blocks for use in the library. So in part A, you're going to be confirming how fast your microchip is running. So we set the chip to run at 32 megahertz. You're going to actually confirm that fact. The way in which you do it is that there's one pin on the chip, pin 14, which is a clock output. So the pin puts out a square wave, and the frequency of that square wave is 1/4 of the actual processor's speed. So the reason why the frequency of this square wave is only 1/4 of the processor's speed is that it takes a couple of instruction cycles for the chip to create this output. So it can't make a square wave that is exactly equal to its own clock speed. The best it can do is it can make a square wave that is 1/4 of its clock speed. So I'm going to show you what this looks like on your breadboard and also on the oscilloscope screen. So to measure the clock output of your chip, first of all, you got to power the chip, so turn that guy on. You're not going to be programming anything, so you don't need the picket here. And to connect what we're getting out of the chip into the oscilloscope, we're going to use this little cable here. The way in which you connect the oscilloscope via this cable to your breadboard is you get 2 little pieces of wire, and this end here has a little sleeve, and if you pull this back, there's a bit of metal there, a little hook. So you can hook a piece of wire in there, release the sleeve, and that clamps the piece of wire. And the other end is just an alligator clip, like so. Now, the alligator clip is the negative end, so you put that into ground anywhere on your board. And the other end, with the sleeve, that is the positive end. That should go to pin 14. Like so. And I will show you in a moment what this looks like on the oscilloscope screen. So this is what the clock output looks like on the oscilloscope screen. As you can see, it's not a perfect square wave. It's a little bit rounded off. You're going to be using the oscilloscope cursors to measure the voltage, the frequency, the period, and the duty cycle of this waveform. And specifically, you're going to use those values to confirm how fast your microchip is running. And with all waveforms that you measure in this lab, remember that you need to record the scope trace in your logbook. So either that means that you draw it by hand on graph paper to scale with labeled axes, or, and this is probably the better option, these oscilloscopes allow you to save the image onto a data stick, and then you can move it over to one of the lab computers and print out the image. But either way, you have to get an accurate representation of what you see on the screen into your logbook, and that's true anytime you look at a waveform on the oscilloscope screen. So in part B, you're going to be revisiting something you did in the last lab. So in the last experiment, you created a program that would blink 2 LEDs on, and the press of a button would cause the LEDs to blink faster. So the signal that you were sending to those LEDs was a square wave, and you're going to look at those square waves on your oscilloscope. So the problem is that oscilloscopes tend to work better at higher frequencies, and the frequencies we used last lab were a little bit slow. So the first thing you're going to do is you're going to go into your code for lab 4 and change it so that the blink rate is 1,000 times faster. So you change your delays. Then you're going to connect one channel of your oscilloscope to one of the LEDs, and the other channel of your oscilloscope to the other LED, and you'll look at both traces on the oscilloscope screen at the same time. And just as you did in part A, you'll be using the cursors on the oscilloscope to measure your voltage, your frequency, your period, and the duty cycle for both of those square waves. And as always, if you're looking at a trace on the oscilloscope screen, you need to put that in your logbook too. So you either draw it or you print out an image off the screen. Now say that you have sped up your code 1,000 times like you're supposed to, and you've set your LEDs blinking at the slow or the moderate setting, and you're now looking at it on your oscilloscope screen, but instead of seeing well-defined square waves like you're expecting, instead you see something like this, where you've just got these tiny little spikes. What's going on? Well, there's something in your code that is screwing up your timing. I know exactly what's causing that, but I want you to figure it out. So if you see something like this on the slow or the moderate blink rate, then what you should do is set up a stopwatch in MPLAB and time how long it takes to execute certain statements in your code. Figure out what's screwing up your timing and then fix it. So before you start Part C, you really need to have completed your pre-lab readings. You need to have read those sections of the chip's datasheet before you begin. What you're doing in Part C is, you've been using the osc.c file all this time to set your chip to run at 32 megahertz. But your chip is actually capable of running at a whole bunch of different speeds, and so your job in Part C is to go into that osc.c file and create new functions that will run the chip at every speed that it's capable of running at. You'll also want to go into osc.h and add prototypes, of course. Then you're going to run the chip at every speed that it's capable of running at, and you're going to confirm on the oscilloscope that it is running at the speed you set it to. Now I'll just sit down here and talk about what they have written in these two boxes. So in the first one, they're warning you that if you're using your LCD also, which you don't need to do in Part C, but if you are, then you also want to be careful that your configure useart function is setting things up correctly between the LCD and the chip. So if your LCD, for example, thinks that the chip's operating at 32 megahertz, and you've actually got the chip operating at a slower frequency, then you're going to get garbage symbols on the LCD. So you just need to be careful that whatever speed your chip is operating at, you correctly tell the LCD that fact. In the second box here, they're telling you that you should run your programs at the highest speed of the processor that is possible, so 32 megahertz for the rest of the course. However, that's not necessarily true for the rest of this lab. There are places where you may want to run your chip at a slower speed in order to get a longer delay than would be possible at 32 megahertz. So in Part D, we're going to talk about the PWM module. So PWM stands for Pulse Width Modulation, and I've got a little diagram to help explain that. Remember when we talked about duty cycle? The duty cycle was the ratio of how long the pulse is high for relative to the entire period of the repeating waveform. So if you consider this on cycle to be a pulse, then the phrase pulse width modulation makes sense. We're talking about making this pulse either wider or narrower. In other words, we're talking about changing the duty cycle. So a narrow pulse gives you a smaller duty cycle, and a wider pulse with the same period would give you a larger duty cycle. So going back to the manual, as the manual explains rather nicely, if you've got an LED and you want to dim it, one way to handle that would be to put it in series with a resistor, but that actually wastes energy heating up the resistor. Another way to handle it would be to turn the LED on and off so fast that the human eye can't detect the flickering. If you do that, then the LED looks dimmer, but you haven't wasted any energy in dimming it. The same thing works with DC motors. You can send a square wave to a DC motor. That turns the motor on and off very rapidly, and when it's off, inertia will actually keep it turning. So the average speed of that motor is then less without actually having wasted any energy in slowing it down. The robots you're going to be using in the final project for this course actually work this way. You'll be given functions that allow you to control the speed of the wheels on the robot. What those functions are actually doing is they're adjusting the duty cycle of the square wave that we're sending to the motors for each of the wheels. So scrolling down here, this is where the manual gets into the nitty-gritty of how you use the PWM modules on your chip. You've got two of them, PWM1, PWM2. There's three functions you're going to use to control this. One of them is close PWM1, one of them is open PWM1, and one of them is set DC PWM1. So close PWM1 does not have any argument, the other two do. So open PWM1 is where you're going to be able to set what the period of the square wave output is going to be. So in open PWM1, the argument is period. And so this is a number you put in, and down here the manual shows you how the chip calculates what the period of the square wave it's going to output is. So it takes the number you gave it, period, runs it through this calculation, and then that T PWM that you see here, this is the period of the square wave that it's going to output. Set DC PWM1 is where you set how long the on cycle of that square wave is going to be. So its argument is duty cycle, and this second equation down here is the equation that the chip uses to calculate the on cycle of the square wave that it's going to output. So TDC is how long the on cycle is, and T PWM is how long the period of the square wave is. But we're not quite done yet, and that's because in these two calculations there's something called the timer 2 prescale value. And what is that? That's something we actually have to set yet. So the function you use to do that is called openTimer2, and it has an argument. And the argument is going to be one of 3 preset values, and they're given down here. They look a little cryptic at first. They're T2 underscore PS underscore 1 underscore 1. The only number there that you really need to care about is the last one. So 1, 4, or 16. And that allows you to choose a prescale value of 1 or 4 or 16. So you'd call this openTimer2 function, give it one of these 3 predefined values, and then you'd open the PWM module. So let me show you the code where we actually do this. So you're given this code as part of this lab, and let's go through this. So this piece of code is called PWM.C. You get this off of the website as usual, and it starts in a pretty straightforward way. You've got your include statements. You go into the main function and you set your chip speed to be 32 megahertz. And down here we set 2 pins to be outputs, and we set them low and high respectively. And then down here is the nuts and bolts of what we've been talking about. So to begin with, you use the openTimer2 function, and you use one of these preset values to set your prescale value to 16. So after you've set your prescale value, then you call the openPWM1 function. And remember that this argument in here was called period, and over here in the comments they actually show you how it all calculates out to a period of 0.4 milliseconds right here. Third thing you do is you call this set DC PWM1 function, and again we've got this argument. This was called duty cycle, and over here again the comment actually calculates it out. And that gives you an on cycle for the square wave of 0.072 milliseconds, and you can calculate out that that's 18% of T PWM. So we've set a duty cycle of 18%. So now I'm going to go back to the manual, but there's one last thing I want to point out before I do that. So right here this comment notes that we've now set things up so that pin 17 is now generating a square wave. So pin 17 is doing that. But if you scroll back just a little bit, recall that we set 2 other pins up to be outputs. One of them has a high output and one of them has a low output. So this is going to become relevant in just a moment. So let me go back to the manual now. So here we are, and I'm going to scroll down to the next part. But as I mentioned, you've got this PWM.C program, which is going to set up a square wave on pin 17 that has an 18% duty cycle and a period of 0.4 milliseconds. You should take this program and make a project out of it, because you're going to use that in the next part. Now this paragraph right here contains some information that's useful for you to know, and that is you can set up a second PWM module on pin 16, but there is a limitation of the chip that you need to be aware of. The 2 PWMs, the 2 square waves that you're creating, can have different duty cycles, but they have to have the same period, and they will start at the same instant. So that's a limitation of the chip just to be aware of. Now down here you have your next 2 instructions, and what you're going to be doing is hooking up a 2-way LED with an appropriate buffer resistor between pin 17, where your square wave is coming out of, and either pin RB0 or RB1. And you're going to be looking at the color of your LED and how bright it is. Now before I say too much more about this, I'm going to pause the video for a moment here and just show you how you set up your breadboard for this part of the experiment. So this is the setup that you use to explore what the program PWM.C does. You've got a 2-way LED, which I've left hanging off the side of the board just so you can see it a little better. And you should have a buffer resistor so that you don't burn out your LED and you don't pull so much current through your chip that you burn it out. So where do these wires hook up? Remember, you've got a square wave program to come out of pin 17. So that leads into my circuit. It goes through the resistor, then through the LED, and then it goes on to either pin RB0 or RB1. Now in this case, those are pins 33 and 34. Remember that RB0 was programmed to be low and RB1 was programmed to be high. So your job in this part of the experiment is to just swap this wire's position back and forth between 33 and 34, so RB0 and RB1, and see what effect it has on your LED, both on its brightness and its color. So now you've seen how to hook up your circuit. You're going to hook up a two-way LED with a buffer resistor between pin 17, which had that square wave output, and either pin RB0 or RB1. And you'll recall that that PWM.C program set RB0 to be low and RB1 to be high. And you swap your wire between these two pins, make note of what it does to the color of your LED and also the relative brightness of your LED. Now recall that with a two-way LED, if you put current through it in different directions, you should see a change of color. And remember that relative brightness should be set by the duty cycle. So you do these two things and you make note of what you see. That means take good notes in your logbook. And then down here, they're going to ask you to explain it. So you're supposed to explain the physics of what's going on. This diagram is very useful for figuring that out, by the way. So it's split into two halves. This half on the left is a pin that's set at 0 volts and another pin that is outputting a square wave. And you want to think about at what point current is going to flow in this circuit. So in order for current to flow, there has to be a potential difference, a difference in voltage between the two pins. So if RB0 is set at 0 volts, then that means that when the square wave goes low, there's no potential difference between the pins, no current's going to flow. So current will only flow when the square wave goes high. And it's going to flow from high voltage to low voltage. That means it'll go from pin 17, which has the square wave, to pins RB0, which is being held at 0 volts. Over here on the other half of the diagram, we've got one pin that's being held at high, 5 volts, and the other pin is still putting out that square wave. Again, current is not going to flow unless there's a difference in voltage between the two pins. So if RB1 is being held at 5 volts, then when the square wave also goes high, there's no potential difference, they're both at 5 volts, no current's going to flow. So the LED doesn't come on. Instead, it comes on when the square wave goes low, because then you've got one pin set to 5 volts and one pin set to 0 volts. So in this case, the current should flow during the low cycle of the square wave. But note that it's still going to flow from high voltage to low voltage. That means it's traveling from pin RB1 to pin 17, the opposite of what it was in the first case. Remember that they're asking you to explain both the color change that you see in your LED and also the brightness change, and brightness depends on the duty cycle. So now back to some actual programming. Scrolling down a little bit, this first instruction tells you to create a program that runs an LED between pin 17 and RB0 that progresses through a series of duty cycles. And this gets a little complicated, so I'll go through it slowly. The first duty cycle will be 0%. The second one will be 33% with a period of 0.2 milliseconds. The next one will again be a 33% duty cycle, except that the period will be longer. It'll be 0.3 milliseconds this time instead of 0.2. The next duty cycle would be 67% with a period of 0.2 milliseconds. The one after that is again 67%, except with a longer period of 0.3 milliseconds. And then you go to 100% duty cycle and back to 0% with the push of a button. So this is just like what you did in Lab 4. You can cannibalize your code, but what'll be different this time is that you'll use the PWM module to set your duty cycles. The current direction doesn't matter for this, but you should check your output on the oscilloscope, and then they've got some questions for you. So they say, for the same duty cycle, say 33%, what happened to the LED, if anything, when you had two different periods? So same duty cycle, different periods, did that change the brightness of your LED? And if you swap in a speaker instead of an LED, do you hear a difference between the two 33% duty cycles? So explore that a little, write down your observations, and you should be able to explain why it's happening also. So in part E, you're going to create a reverse gear for your circuit. So you found in the previous part that if you switch the polarity of the RB0, in this case, if you went from low to high, that would change the current direction through the LED, so it would change the color of the LED. However, you also discovered it can have an effect on the brightness of the LED because it effectively changes the duty cycle. So your job in part E is to have your circuit set up such that one button, when you push it, will cycle the brightness of the LED, And the other button will change the color of the LED without changing its brightness, so without screwing up the duty cycle.